Uh, Hello, here is Mohammed Zanetti. I'm a postdoc at Harvard University, and for today I'm going to present my work with Dr. Vardi and Professor Hiнаin on tuning stiffness nonlinearity in compliance structures. I will go first through the theory and then applications. So the topic of stiffness tuning is common. It's used a lot in robotics for various applications. And if you look in terms of stiffness tuning in compliance structures, there are two main techniques to implement that. The first one is related to modifying the geometry. So for example, you have a cylinder beam and then you will have a slider. And as you move the sliders, the effective length of the beam will change, which will modify the stiffness. The other technique is related to imposing loads. A simple example is also a cylinder beam with an axial load. And as the axial load changes, the effective stiffness of the beam will change. However, there is no study so far which related to tuning the nonlinear behavior of compliant structure independent of the linear behavior. As in all these cases, like geometry tuning, imposing an axial load, in all these cases, both the linear and the nonlinear behavior are modified. So for our presentation today, I'm going to present like three different structures to modify the nonlinear stiffness independent of the linear stiffness. So if you look for the first method is based on having two springs orthogonally connected. So in this case, we have K0, which will represent our nominal stiffness, and K1 and K2, which are connected in the orthogonal direction. And as we initially pre-stretch K1 and K2, we can tune the nonlinear behavior. We got like a very simple equation here, which describes the stiffness behavior. And as you can see, the nonlinear behavior is a function of D2. However, the linear behavior is independent of D2. The second case is related to having two springs connected in parallel. And as you impose the displacement x, the effective stiffness will be a function of alpha. And as you tune alpha based on this equation, you will tune the nonlinear behavior. And the last case is related to having a cam with non-uniform geometry, and it's connected in an orthogonal direction to a linear spring. And based on the geometry of the cam, you will tune the effective stiffness. And to verify that, we selected the orthogonal connected springs. And in this case, we have two tuning input, D1 and D2. And by looking for the different stiffness values for different D1 and D2, we have four regions based on the sign. So this structure can show a nominal positive stiffness or negative stiffness. And also it can show a hardening or a softening effect. The special case occurs at D2 equal to 0, because at D2 equal to 0, the nominal stiffness is constant. It doesn't change as we change D1, but changing D1 will lead to a significant change in the nonlinear term. So for example here, if we look at D1 equal to 0, you can see that we have a hardening effect. If we look at D1 equal to 0.3, we will have a softening effect, even like we can see there is a negative stiffness. However, if we look at 0.1, at the value of D1 equal to 0.1, here we'll have a linear spring. So D2 leads to zero nonlinear stiffness term. As an application, we start looking for programmable metamaterials, and also this kind of behavior is very useful for isochronism tuning in watch oscillators. And finally, we can use it to implement different logic gates. As you tune the nonlinear behavior, you can change the gate from being an OR gate, for example, to an AND gate. Further details can be found in the manuscript, and if you have any question, please reach to us. Thank you.